right, there you go. So this will be recorded.
Trinidad and Tobago.
No, that's it. That's Carice. All right. Delete. All right, so yeah, I think we're live. Yeah. What's that? Carice is still not seeing anything?
Yes, sir. I'm seeing everything.
Okay, good. All right, so this is the setup for the lab. Let me even post this. All right, so all right, yeah, just trying to send out these messages then. All right, no, so now it's in the screen. All right, so all right, the apparatus that we use in, you would want to write them down in the apparatus. So I'm gonna write them on the screen. So when you switch the screen, so you can see the paper, the lab sheet that is, then you will know what to write down. So this object here, let me just zoom in. This, what does this look like to you? Or tell me some of the equipment that you recognize here. What is Tiffany and Carice?
Yes, sir.
I'm saying to tell me the equipment
Yes,
that you
sir.
recognize. Yeah, go ahead.
Sir. A B.
Yes.
Sir, one test tube.
Test tube. You love that word. Where is the test tube? Show me where the test tube is. All right. So, hmm?
Hello.
All right. Certainly.
Sorry, I hear me, sir.
Yeah, I'm hearing you now.
Talk, sir, because the phone, the laptop, very reconnect.
Okay. All right. Um. Let's see. I'm just writing down all of the equipment that you're supposed to have in your data. Then. All right. So just write them down. All right. So now what you're seeing here, what you should be seeing is a large tube with water. All right. This is actually the resonance tube, and then you have a tube, and you have a tube inside of it that has some markings. Right. So this is actually both of them are cylinder, but then you have one inside and one outside. All right. So if you're seeing that, then that's what it is. All right. Now, so if you have the lab sheet now, you should see the steps here. And the step that we're using here, we say pick a tuning fork with a frequency and strike the fork gently and hold it at the end of the resonance tube. So we're just going to carry this out and see what happens here. So we want to go to the tuning fork. Right. Tuning fork is basically a metal fork that makes a certain sound when it is hit. And that sound that it makes is dependent on the frequency of the fork. So as you can see, we can use this. We can use 256 hertz. We can use 384. We can use 400. We can use 426. We can use 512. We can use 1024. All right, and of course there's an unknown here. All right, so that's where. So then we're gonna adjust it. When I start from 256, and when I hit disturb, and as you realize that it's hit and placed over the tube. Now what's gonna happen is that the sound is gonna travel through the tube, all right, and it's going to, when the sound waves will bounce, all right, it will bounce at the end of the tube and come up back. All right. As a matter of fact, we should be moving this. All right, let's see what the step says. All right, so we strike it, guys. Them say vary the length of the tube by immersing the cylindrical glass filled with water. So again, the end of the tube, guys, is actually, everybody, you see that? Let me share. Let me see if I share the screen. It's supposed to be hearing something, so I'm going to put on the sound so you can hear it. All right. You hearing anything?
Yes, sir.
All right. That what you're hearing is actually resonance. All right. That is called resonance. All right. So resonance now is, see that sound there. So we hit the fork first, guys. We hit it. And we hit it at the frequency. When we hit this fork, it produces a frequency of 256 hertz. And then that sounds like this really. So let me just keep moving it again. So this is what it really sounds like when it is when it reflects. So we strike, the sound wave comes in through the cylinder, and we'll move it and find, is that that's actually, that's what we call an antinode there. All right, we're and that's what we record. All right, let's see now. You can click record data. That's the next thing to do. When you hear that sound though, when usually we record the measurement there. So we want to get the measurement. And there's a reason why we're going to get that measurement. We'll show you that afterwards. Bear the length of the tube by immersing it in a cylindrical glass filled with water. Record the reading L. All right, when the sound is quite loud. So what we're doing is looking for the length of the loudest sound. As you can see here, if we zoom in, we can't zoom in anymore. We're seeing it's about what? 20 something. Yeah, 20 is about let's record the data and see what it looks like. All right. Reset. All right, I think the results should be there. No data collected. Like if I go write it down yourself then. All right, so let's carry it down to 256 again. We're going to reset this again. All right, so watch this again now, guys. Disturb means we're going to hit the fork, make it make a sound. All right, that sound now, we put it over the tube now and we listen for the what we call the resonance, which is the sound repeating or echoing in a sense. Loudest sound will tell us the wavelength of the wave, which we're going to write that down. All right, so in the table, let's see if there's a table here. Yeah, there's a table on your lab sheet. We're going to write down all of that. Length of the column is gonna be looks to be right here to be 20, about 20, probably about 25. Is it? All right, set the sound here because it's not going to be 25. Looks to be 25. Let's turn on that sound here. All right, this is 20, 21, 22, 23, 24. It looks to be 25. So we're going to write 25 of that's the length that we heard the sound, the loudest. Remember, it sound the loudest because it has to do with the wavelength of the wave that we made. All right. So now, the frequency of the fart now is going to be 256. And that's all I'm going to know. Use another fact, do the same thing like I did a while ago, guys, and record the result. So it's a relatively simple app. Let me just put in some more lines so we can get about five values here. All right, so 25, about that, 256. All right, we're reset now, guys. We're going to go to 384. Do the same thing. All right, well done. Look at that. That sound different. See that 384 hertz sound different from the 256 that we use. Notice that this one should have a higher pitch. And that's where slow this there. Yes, go ahead.
My internet coming on.
What's that?
Come on.
This is about your internet?
My internet is on and off.
Yeah.
So when we come back, I'm not.
Okay. Okay. All right. Can what?
It is stressing me out.
So what you gotta do now? I'm tell you, do. Well, the video is being recorded as we speak, you know. So you can just download it afterwards. All right. So just try and catch as much as you can now. Okay. All right. All right. So 384. Hit it again. And then we're going to listen for the resonance. Right there. Very loud. All right. So if we're going to take off a measurement there. Probably record it for still. Look like 20 something. Probably about 23 and a half. All right. Reset that. Not seeing should be recording the data, but let's see what happens afterwards. All right. So we're going to write down all of the frequency we'll use. Now we're going to 400. 400 is the next one. Remember that the frequency will be increasing, right? So after 400, we're going to go 426, we're going to go 512, and we're going to go 1024. All right, so Let's go to 500. Actually, this is 512. Let's see what happens. It's gonna be 512 after, or rather 426. Yeah, definitely 426 here, guys. All right, so 426, and we have 512. Because, testing each of these sound waves. And of course, 1024 will be the last one. All right, so all right, so we're getting there, guys. All right, so at 400 now, do you have anything for 400? How about 23? We'll put 23 there. And then what we're noticing here is that as the it should be that when the frequency of the fork increases, the length of the tube should decrease. So all right, that is the measurement on the tube that should be less. So at 400, looks to be, here's here. All right, Carice is here. All right, so at 400 now. Zoom out this one. About 20, well, less than 20. This look like about 19. That's the loudest one here. So when it's 400, it's about 19.
Sorry, sir.
What's that?
Sir, like 18.
Like 18? All right, we could go again. Probably yours better than mine, so let's go. Reset it and try again. 400, go 400 again. Disturb it. See, like about 18. Now we carry it all the way up, we don't hear it. We carry it all the way down, we don't hear it, but
Stop.
so remember that. Well, you say that's 18. Could it be? It looks.
Hold on there, sir. Sir, which
Right, that's so.
sir, pause the 20 line.
Past 20. All right. So yeah, we can call it 20.5. All right. Okay, about R20 then. If we're sure about that. Past the 20 line, 21. Apparently it's 21, About 21 that. All right, we'll call it 21. Hopefully this software record the results as we go along. All right, so let us reset that. Put back the fart there, and I'm gonna go to 426. Or was that 426 a while ago?
400, sir.
It was 400. Okay. Let's confirm that then. Yeah, it's about that. That's 400. All right, so let's just reset then. 426 now, guys. Want to see how that sounds and what measurement we get for the wavelength. All right, so let's disturb it. 426. Put it over the tube. Notice that this one has a higher pitch, higher tone. You'd want to say about there. So that looks to be at the 20 mark. At 426.
Yes, sir, 20.
All right, good. So let's reset that then. And it's going to go to 512. So we have 512 and we have 1024 to do. All right. So disturb. All right, hit it now. Again, a higher pitch sound. We're getting a nice resonance right there. Even have to just turn on my computer because this sound is loud. All right. So that sound, the measurement now looks to be a few a few centimeters less than 20. So this is 20 here. So 20 is right there. This line there, and this will be 21. This will be actually 19. Um, looks to be about 18, approximately. Let's put 18 there. We can always looks to be 18 though. And the measurements look like they're going down by 2 each time or something like that for the length. All right. So let's reset this now. And we're gonna go to 1024. All right, again, this is it's supposed to be a higher pitch sound than 512. So let's disturb it, hit the fork, and definitely a higher pitch sound here. When it all the way up, you don't hear it, but carrying it down about there, we hear that. So this looks to be a very very small measurement compared to the rest. This looks like what? This looks like about 8.
Look, 7.
It looks 7. All right.
And
We just put 7 then. And then we have results here. So all right. There is an unknown frequency. This is something here. No, we can just leave it at that. All right. So that's unknown frequency, but we don't have to trouble that because we have 6 results already in the table, so we can work with that. All right. So let me switch the screen now and let you see the data. As a matter of fact, maybe I should go ahead and collect the last one and see if it records the data for us, because that's how this software tend to work. So let's disturb it. All right. All right. All right. Let's just try. Somewhere up there. So harmonic there. This one is somewhere. All right. All right. So then, and this is finished. All right. Now, can I get some data? I'm not seeing the data here. It look like I would need to press through these. All right. So we did number 1 and number 2. Vary the length of the tube by immersing in a cylindrical glass filled with water, which is this clear tube there. Record a reading. All right. Record a reading L when the sound is quite loud. So we did that a while ago, and that the length of the tube. Record the length of the tube. Change the tuning fork and repeat the previous steps. Plot the relation between frequency and 1 over the length. From the slope, find the speed of sound in ear. And there we go. All right, so that's the instructions. Very simple instructions, guys. And I'm saying I'm not, for some reason, I'm not seeing the results. All right, well, anyway, we can get our own results then and erase that. All right, so when you switch the screen now, guys, let you see the data that we collect, and we can finish the lab from there. All right, so see the screen, Tiffany and Caris?
yes, sir.
All right, so this is the data that we have so far. All right, and then we're going to have to plot the graph here. All right, now let me just add the graph paper. Mm. All right, so there you go. That's what we're using. All right. So question is, how would this graph look on a graph paper? And expecting a straight line. Let's probably, how can I get to group this? Group, no group option. What I really do it with this thing, show me the record, the data here, but it's not. Oh, hold on a sec. It have a PDF. Suppose they can give me one printout, you know. Hold on a sec. Yeah, so yeah, I'm not sure what's happening. All right, well, this thing take a Ghana. All right. Anyway, so we're not getting anything from the lab in terms of the data. We have to use our own. We're going to try and get these results on the graph. All right. So them say we must plot this. This is where you're going to get some marks from now, guys. It's a plotting the relationship between the frequency and 1 over the length. So what that means now is we need a column for 1 over length now. All right. So we're going to do that here, right beside, and it's 1 over length, right? So that's 1 over L, because that's what they tell us to plot. And then this would be actually meters to the -1. Actually going to be centimeters to the -1. We have to do some conversion here though. But let's convert it. 1 over 25, and it's going to be 1 over 23, 1 over 21, 1 over 20, 1 over 18, 1 over 7. All right, that's the results you're going to have. All right, so 1 over 25 would actually give us 0.0 what?
4.
0.04. Okay, that's Stephanie. All right. What does 1 over 23 give us?
0.043.
Okay. So 0.043 and okay. I'm seeing it now.
Sir,
Seeing it, yeah.
0.04347. I'm really off now. That is 0.0435.
Okay, let's just keep it at 0.043 then. All right. All right. And then 21 would be what?
0.05.
Just run it round off.
Yes, sir. 0.047. So round off and say 0.05.
Got it. 0. What do you call it? 0. 47. It says 0.047. I forgot to put that. I forgot to use 3 decimal place. All right. So yeah, we're all right. We can fix that, man. This will be 0.050. All right, give me 1 over 18 now.
0.055.
Okay. And 1 over 7 supposed to give what? 0.1, 0.16.
0.142.
Okay, yeah, okay. All right. Yep. So we have a result in. All right. So certainly you get a mark for actually converting these into decimals here. Remember, you're going to plot the F, which is these numbers over here, against 1 over length. So we're going to go to the graph paper and secure the marks for labeling the axis, because here now, remember I was saying we're plotting F which is frequency, versus 1 over length. And if it's 1 over length, it's going to be 0 there. This line is a 0. So this y-axis will be used for frequency. And frequency is measured in hertz. All right, the 1 over length now is going to be, this is a interesting case because we want the length to be in meters. Remember, the wavelength of a wave is measured in meters. And we're going to have to convert these readings into meters. So I would tell you to go ahead and do it, but you know, I don't know if you can do that. So I'll just do it for you. 1 over length is so basically what we have are these measurements. It's just a pity I couldn't. And if I could can get a copy here, it'd be nice to really have that results here. Not allowing me to group at all. All right, I can save it as a picture. And let's go data. Data for all right, and that's saved. Let's go over here now. Let's F11. All right, I'm going to try to locate that paper, those results. Let me see if it's here. I'm going to drag it over here. Hopefully we can see it. Yeah, we have it. All right, we have it. All right, so I want to get these results closer to us here. 1 over length, that part might be, it might be a bit tricky for you guys. So we're going to put the readings in meters to the -1. Now, first of all, we're going to have to convert the centimeters to meters. And that's where the catch is. So we'll have to, again, when you convert from centimeters to meters, what them teach you in 4th form or even 3rd form is that you divide by 100. So basically what it means is that we have centimeters to the -1 here. No, we want it in meters to the -1. So we have to divide all of these by 100. So this is 0.04. What we're going to do to prevent all of that work is when you use standard form. And if we divide 0.04 by 100, we basically going to move 2 more decimal places to the left. And so that will give us 0.0. Well, 0. All right. And it's going to be 0.40. So it would be decimal point would be here. Oh, sorry. Yeah, 2 zeros, huh? 0.00. Yeah, that's what it would be. So this would be meters to the -1. So we're going to fix this easily. We're going to treat this part as whole number. This scale down here, the x-axis, we're going to treat it as whole number. So in order to do that, we can move the decimal place right there. Right? And that, what, 1, 2, 3, 4. And we're just going to call this 10 to the -4. All right, so at this stage, you should know what we're doing here. We want to spend time into that. But what it means is that whatever reading you have in what we went, so you're going to basically use all whole numbers here. We can start from like 4 and maybe well, yeah, we could start from 4, but then you have 4.3 there, so this is gonna be a bit tricky. We have to we'll have to find a scale that can hold 4.3 and 4.7 and 5. It's going to go actually from 4 to 14, so that's not bad. All right, we have a idea here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this would be 8, and then we'll have 12, and then 14 would be somewhere there. So we can use this scale. All right, what you probably can use on your graph paper is 1 centimeter to 1 unit. All right. So anyway, so let's put in the numbers in. 1, 2, 3, 4, 5, 6, 7, 8, 9, hold on, 9, 10, 11, 13. And that's where we have that. So remember now, we're going to treat this as 4, not just 4, but it's 4 times 10 to the minus 4, if you see that. All right, this would be 4.3. This would be 4.7. This would be 5. This would be 5.5. And this would be 14.2. All of this is times 10 to the minus 4, which will give us the same number that we get here. All right. So there we go now. We have all of that. We have the length part figured out now. Any questions here, guys?
No, sir.
All right. What the hell is happening here? I think this something is happening here. We'll close up some of them here. Which I don't want to. Oh. Yeah, it's like I got some internet problem. Let me see if it's. Yeah. All right. So when I save this, it's completed. All right. There we go. And I'll group everything and move it across. All right. So we have the results here to work with. Let me see if we can get to crop this. No. All right. No problem there. Everything good. All right. So we're starting out that part now. We have the length part. All right. Now we need to focus on the frequency, which that part now is going from 256 to we have 512 there. So we're going to do this now. Find a nice scale there. Probably can go up by 100. So we have 100 there. Every 2 centimeter will go up by 100. So this is 100. Next 2 box will be 200. Next 2, 300. Next 2 will be 400. Next 2 will be 500. And that's the progression here. 600. It'll be 700 there. And it's going to be 800. And we have 900. And then here we go, 1000. That's it. And then we have 1024 in between there. So basically now we're going to find 4 and link it up with 256, which up here says 250. So I'll be somewhere there. Somewhere of this. In fact, very close to. And we can just move this a little lower. All right. So now 4 with 256. 4.3 now would go to 384. All right. So 4.3 now somewhere close to this. All right. So 384 will be somewhere. Well, here's 350. And here will be like 4.3. So pretty close to the 400 mark. So that put an X just about there. All right, 4.7 now would be pretty close to 5. And 4.7 will go to 400, so that's easy to find. So these readings here, and what this is saying is that, well, we need a good scale on the graph paper to get something out of this slab. We should get a straight line though. That's what we're aiming for, straight line. So soon line it up afterwards. All right, 5 will go to 426. So this 5 will go to 426. This graph will look weird. All right, and then now 5.5 will go to 512. 5.5 to 512. 512 will be somewhere there. And then what I'll do now is zoom in so you can see how the points really look. All right. And then, of course, 1024 will go to 14.2. So this will be all the way out here. All right. So remember, 14.4 would be here. And, of course, that will go to 1024. 1024 is all the way up here. It's an interesting graph. 1024 would be 19, man. Scare all the way up there. Yeah, sorry now. 1024 would be somewhere up here, close to 4 to the 1,000. 14.2 would be like over there. So, and that's our graph. All right, let's see if we can insert. Let's have an idea with the ruler now. Can use a ruler to see what's happening here. This one. All right, let me zoom out. Now give me no option for turn this thing. Let me just remove this down, man. No work out. All right, we're gonna use a line then. Let's get a line to connect these points since we're not getting the ruler. The line we're going to stay. In fact, the line of base fit is what we're looking at. So line that we pass through all the points, but it can certainly can get something out of it. So why is this not okay? So I'll stay something like this, you know. Let me see, I'll get 2 on one side and 2 on the other side. Right there. Yeah. Right there, guys, right there. All right. So yeah, this is all line of base fit. So your graph going to look something like that. So there you go. When I find the gradient, let's go back to the readings here. Find the slope or the gradient speed. That will give it a speed of sound in ear. All right, let's see if we get an accurate answer. All right, so the speed of sound in ear, guys, should be around something close to 340 meters per second. And that's how we can know if these results are accurate. So what we're gonna do here now, we're going to use a line. We could do something like this. Remember now, we can use 2 points on the line that are far away from each other and form a triangle with it and actually get the gradient of the line. So it's gradient of the line there. We use numbers that we have. So this number here actually would be 1050. So there will be 1050 there. Remember that gradient is equal to rise over run. So gradient is equal to rise over run, or y2 minus y1 over x2 minus x1. Let's find out what these numbers are. So so this would be our y-axis now. So this would be our y2, and then down here would be our y1. Y1 will be 250. All right. And y2 would be 1050. So we'll have something like 1050 minus 250 over what we have here. This looks to be 3, but then actually this will be our x1. This would be 3 there. And this is our x2, which according to this would be 13. So we'll have 13 minus 3. And this is looking like an interesting answer. Let's see what we should get. I remember we're looking for something in the region of 340. But when we do 1050 minus 250, that should give us about what, 800?
Yes, sir.
It's going to give us 800. All right. Now let's take a look at the units. This frequency is in hertz. And of course, this wavelength here, it's actually 1 over wavelength. So symbol for wavelength is lambda. All right. So this would be hertz, but this would be in per meter. So now it's interesting units, but as a CAPE level, you should know how to treat that. All right. Now 13 minus 3. So this is actually going to give us 800, which is a very very far out answer, really. Not the answer we're looking for. Very far from the answer we're looking for.
Sir,
Yeah. Yes, go ahead.
so you say, sir, now divide 800 by the 10.
Yeah.
So you get 80.
How much did I
So you
get?
have 800.
80
get
again.
sir.
Yeah, it's gonna be 80, yeah. And this is far from what it should be. So but again, I think what happens here is that this is not an accurate graph paper. So you'd have to do it on a real graph paper and find that out. But I'm just showing you how to do the graph. So you know what to do when you get a graph paper. All right. So I mean, this is what we get. Definitely far off. But this is what the graph should look like. Certainly if I did this and handed it in as the IA, I would lose marks. I wouldn't really lose any marks, In fact, the only thing that would be what I'd have to do here. The next question asks, see, they determine the slope of the graph and hence the velocity of the sound wave. So we just do that a while ago. So just put like C graph paper. So that's done. All right. Now fractional uncertainty in the frequency of the tuning fork. This was not given. So therefore, we're not using that. This was if the lab was done face to face. But certainly this would be our part B here. The fractional and percentage uncertainty in the speed of the sound wave. All right. So here's what's going to happen to us now, guys. The uncertainty, is actually the experimental value. All right. In fact, you're going to have the true value minus experimental value over the true value. And it's actually going to be times 100. All right. So basically, that's what's happening. All right. Now, how this work out now? The true value, speed of sound, true value. If you look up on the internet, it will tell you. As a matter of fact, let's do it right now and see what result you get. That's a true value. It's the speed of sound value. So they're just close to 340, but again, it depends on the temperature. They have 343 here. So and that's according to Google here. It's 343. So close to that 340 mark. But we're going to use 343 then. And this lab has so many limitations. 343 minus the 80 that we just got over 343. Again, times 100. This will tell us the percentage uncertainty there. Percentage error. All right, so if we take away 80 from 343, you probably will be left with
263.
3 what? 363?
263.
263. All right, very good. So 263 over 342 times 100. Very high percentage error here. Whoa. And then this will be from my experiment, but yeah.
Sorry, 342 or
343. 343, man. So 343. True value minus experimental value over true value. Yeah. All right. So 263 divided by 343 give us what?
0.7667.
767. All right. This is the fractional uncertainty, 0.767, you say? Percentage uncertainty now, you don't multiply that. So that would work out to 76.7%. That's a high error. They recommend doing over this experiment. But then again, that's only because I'm not using a real graph paper. So that's the issue there. All right. Then you're going to use a real graph paper and get a much better answer. All right. Any questions?
No, sir.
All right. All right. As well as the data, because we didn't we didn't get the printout from the lab itself, then we have to be estimating. So we're going to have some source of errors there, which we're going to account for. All right, so these are things you're going to have to research now. What is meant by wavelength? What is meant by the term frequency? Resonance, all of that is on the page here. Resonance here is induced vibration in an object. All right. And induced vibration due to the resounding. All right, due to the resounding of a sound. So all right, it's really what we heard when the sound appeared to have gotten louder. After you strike the fork, it make a sound, then the sound resonates. So it went through the tube and it came back with a louder sound. So it's almost echoing what you did. All right, so that's it. So we have these to research and put in the answers. Resonance is there, and that will be on page 3. All right. See it all each term apply to the experiment. All right. The terms wavelength, frequency, and how them apply to the experiment. Okay. That's easy. Wavelength is the length of the tube. Oh, you know, see what happened now, man? Let's see what happened now. So you can get the right answer. Never realized something. One. If we did a 4L, let me see something. If we get the right answer. Let me say a wavelength, a 4L. So we could have multiplied the answer by 4. Could I multiply answer by 4? If I multiply answer by 4, would I get it? 4 times 8 now, 320. Would I get it, you know? All right. Let's figure out what we're going. That's why I'm right this way. All right. So wavelength is equal to the length of the tube times 4. All right. So, and then of course the frequency now. Frequency, how it applies to the experiment, what you mean is that each had different pitches, tones or pitches. All right. So the term applied, the length of the tube is actually 4 wavelength length of the tube times 4. And this is, yeah, and that's equal to wavelength. I forgot to talk about that then. Explain the propagation of the sound wave from the tuning fork via the human ear resonance tube. All right. The answer to this is here. The answer to this is here. So all right. So basically what happened here is that go back to the question and confirm what it's asking. Whole heap precautions here and source of error, but propagation means how the sound travel. So how the sound travel from the fork. That's the question that you're asking. All right, so basically let's summarize it. Go to the fork and hits the water surface. Then it reflects, comes back, reflects towards the ear. And this is our reflection. Reflection. All right. So now, what you don't know, you adjust the tube. So adjusting tube. Adjusting tube affects the loudness of sound due to resonance. All right. Oh, and they actually have your expected value, which is 3. But then we're going to change the expected value for this. It's actually going to be 343 for this one. And let's see 3 for it. Yeah, that's 20 degrees. All right, so let's see. So guess what? So it's actually calculation would have been incomplete here because this 80 that we got, this 80, if we go back to the table, we see that wavelength is actually equal to 4 times L. Now, let me show you this now. Remember, I said this is the frequency, and this is just L, or in this case, 1 over L. So therefore, we never finish this part. So therefore, since the formula for speed of sound wave, all right, speed of sound. Let me just write it maybe somewhere else here. All right, so since the speed of sound V is actually is equal to frequency. And you should know this from CXC times wavelength. All right. Then is this one? Sure. All right. So the speed of sound here is it. All right. Now watch this now. The wavelength. But we say wavelength is equal to 4L, length of the tube. So we have L naught L is equal to 80 meters per second. What did I do there? Let's write it 80 meters per second. So 4 times 80 gives us wavelength, which in this case, 4 times 80 should give you 320 meters per second. So that's where we should have start this thing out. All right, so now I'm saying I missed somehow. So that's what I have there for the wavelength, 320 meters per second. Yep. And 320 are the answer, not wavelength. So velocity. And this will be velocity. So this will apply for the wavelength. All right, so all right. So 320 would be the answer, really. So we have to go fix up that. Yeah, you can do that. We can always do that afterwards. But anyway, that's the idea, guys. So this list this basically is complete, you know, in the sense that we just need to that source of error. Source of error now would be, of course, we whenever I have the readings here, measuring the length of the column. All right, precaution, you know, we're going to know. I just tube to the loudest. Sound was heard. Of course, limitations, temperature, the virtual lab, algorithmic errors and limitations. And we're gonna put that 320. All right, and so this is it. So yeah, so you can go ahead and write this up, guys. Any questions?
So where's the diagram?
The diagram is on your lab sheet that I sent you.
Oh, all right then, sir. Right, sir.
All right. I'm going to send this, yeah. All right. All right. I'm going to send this in the group now. Wrong folder save now. I'm supposed to be physics folder. All right. I'm send it. No. Yes. Is that Caris?